Hello. This is the second part of Module 3, which talks about isomers. So let's check quickly what are isomers. So isomers are compounds with the same formula. And we have different types of isomers so far. We have what we call the constitutional isomers. And we have the stereoisomers. So in Module 3, we're focusing on the stereoisomers. So what is constitutional isomers? They have different connectivity. So they have different connectivity. So basically, if they have different connectivity, they were going to have very different names and everything. Pretty much, they're different compounds, but they have the same formula. So that's what isomers means. They're compounds with the same formula. If they have different connectivities, they're constitutional. But if they have the same connectivity, but different spatial arrangement, so here, that's the key thing. We have the same connectivity, but they have different spatial arrangement. So the whole key thing is here spatial arrangement. Now, since they have different spatial arrangement, we have two types. The first type that I covered in the first part of this module are called conformational isomers or conformers. So conformational isomers, they're also called conformers. So what are conformers? They are the same everything, and they have different rotation. So they're due to rotation around the CC single bond. So the one thing about conformation is they cannot be separated, So there's no way you can separate them. And if you remember, we are talking here about the eclipsed and staggered. And if you remember, the Newman projection. We also talk about the chair and the boat for cyclohexane, and how you can flip them, go from one form to another, and that's part of chapter 3. So all this part right here is the end of chapter 3, which is what I did at the beginning of this unit, this module. The reason I put it here, it's because it really falls into this diagram. So what's left then in chapter 4? In chapter 3, the end of chapter 3, they're talking about conformational isomer, and we saw the CC, we did the projections, Newman projection, we looked at the chair and the boat, we looked at the axial equatorial. You need to know all of that stuff. But then here, what are the stereoisomers that are not conformational isomers? They're called configurational isomers. Configurational isomers. So what does that mean? See, there are too many words here. This is conformational. This is constitutional. These are stereoisomers. These are configurational isomers. So make sure you understand the difference when these terms are described. So what are configurational? The key thing you see here, we say cannot be separated. they can be separated. But when you look at them, you're not going to know, how am I going to separate them? So how do I know by looking at them which ones are conformational, which ones are configurational? Well, if to go from one form to another, you literally have to break a bond, then they are configurational. So going from one isomer to another requires breaking bonds and restructuring it. So it requires putting them together in a different way, even though in a spatial arrangement. So we'll get there in a minute. But within these configurational isomers, we have two categories. We have the cis-trans, which can also be E and Z isomers. And we have the isomers with asymmetric centers. So isomers with asymmetric centers. One or many. So that's the focus of this presentation. What are configurational isomers? We'll start with cis-trans, and then we'll end with the isomers with asymmetric center. And since I put an S there, it means there are different categories. You might have one or two or many asymmetric centers. So the key words here, we're going to focus on what is E, what is C, what is an asymmetric center, and how are they similar, how are they different. So let's start with cis-trans, because these are kind of easy to understand. So here are some examples of cis-trans for you to see. So I can have something like this. If I have a 4-atom ring, let's say, and I put a wedge here with a Cl and another wedge here with a Cl. We already saw this in the previous presentation. A wedge means it's coming in front, out in front of this play page. If I put dashed lines, it means it's behind. So you see that both of these are on the front, in front, so they're on the same side compared to the plane of this ring. So if they're on the same side, this is called cis. If they're on opposite side, so one will be coming in the front and the other one is in the back, this would be trans. So they're not on the same side of this ring. So there is a plane. Every time we talk about cis-trans, we have to local to see where is the plane we're talking about and how are the substituent in relation to this plane. So here's the plane, is the 4-atom ring. These two chlorines are on the same side, so that's cis. These two are on opposite side of the plane, so that's trans. Another example would be this. So let's say here I put a fluorine, and in here I put bromine. And I just picked this one to kind of explain. It doesn't have to be the same substituent. Any kind of substituent will do. And here, compared to this one, I can put the F in the back and the bromine in the front. So this is also cis, and this is trans. They're on opposite side of the plane of the molecule. Another one would be this. So here, the plane of symmetry, so you see this is the plane that we are looking at the substituent above and below, same side. In here, we can use this plane, and which is perpendicular like this. So you see that on this side you have H's, on the other side you have the substituent. So here they're on the same side, so this is called cis. And in this scenario where I put the CH3 on top, and the H here, the H here, and the F here, This is trans. Now, I want to mention again, to go back to what I mentioned here, we said there are configurational isomers, and I told you that to go from one to another, you have to literally break a bond. You see here, in order to go from here to here, there is no free rotation that will change this from the front to the back. If this goes to the back, this has to also go to the back. So in order to go from one form to another, you have to break this bond and attach it differently. Same here, same here. That's why they're considered configurational isomers, which means that you can't go from one to another without breaking a bond and reattaching it in a different way. And all of these can be physically separated. They have different physical properties. They might have similar chemical property, but the physical property are different. See how this one is completely non-polar, very symmetric. This one will be slightly polar, not completely non-polar. And you can see it same in here, same in here. They might end up with slightly different boiling point, different polarity. So you can separate them using these physical properties. Now, what if we have something like this? C, double bond C, Cl, Br, H, CH3. Now you see here, I can write the Cl, the CH3, and then H and Br. So you see that these two are completely different. The Br here is on the same side as the CH3. The Br here is on the same side as Cl. So is this a cis or a trans? And the answer is neither. It's not a cis, it's not a trans. So there's a new way of naming or at least labeling these compounds where we can't use cis or trans. What are we going to use here? So this we have to use the E and Z system. Okay, so in this scenario, we have to use E and Z system. So you can't use cis-trans. So when do I use cis-trans? When I have H's. If the H is on one side and the other substituent are on the other side, that's a cis. If your H's are on opposite side, it means your substituent are on opposite side, so that's a trans. So cis-trans applies when you have same substituent on both carbon. So it could be H's, or can put CH3 here, CH3 here. So anything that is identical on both carbons can be called cis, and opposite can be trans, as long as they are the same kind of substituent. But in here, we have 4 different substituents. So how are we going to name it, cis or trans? Well, the rule says, there is a rule for these things, and you're going to call it E or Z. So how does it work? The way it works, you have to prioritize your substituents. So what does it mean, prioritize your substituent? You look here, C, C, Cl, CH3, and you look here at Br and H. So you focus on one carbon at a time. So I'm focused on the pink one right here. The pink one has a bromine on the top and an H at the bottom. So I need to prioritize these two. The green one has a Cl and a CH3. So we need to prioritize them. What's the rule? The rule says the greater the atomic number, the higher the priority. So if I look at this carbon, which of these two, the chlorine or the carbon, so that's what you do. You look at the atomic number of the atom directly bonded to it. So which one has a higher priority? Which one has a greater atomic mass? The chlorine is number 1, and the carbon is number 2. So on this green carbon, this is 1, this is 2. On the pink one, the heavier one is bromine, so that's 1, and this is 2. And the rule says if your number one is on the same side, it's called Z. So if your high priority is on the same side, it's a Z. So this is the Z isomer. Now, if I look at the other compound I put earlier, so here, this is my number one, bromine is 1, hydrogen is 2 for the pink one. I'm using color so you can follow me. And then for the other one here, this is 1, chlorine is heavier than carbon. So you see the one are opposite from each other. They're not on the same side of the double bond. That's what we mean by same side, is that plane. So this is the E isomer. So if your number one are on opposite side of the pi bond of the double bond, then it's an E. If the number ones are on the same side, then it's a Z. So let's practice a little bit more with this. And I'm going to go a little bit fast, but I want you to go through all the detailed rules on page 148, 149, because I don't want to spend too much time repeating what's already very well explained on in your book. So how do you prioritize? I'm going to use some examples here that are important. So if I have C double bond C, and in here I have a CH2, and in here I have CH2, CH3. On this side, I have a CHO, and on this side, I have an OH. So the question is, how do you prioritize these? Well, let's focus on this side of the molecule, the right side. This is my carbon. I need to prioritize this or this. So at the first level, they both have C's. So in terms of atomic mass, it's the same. The second level, you might say, oh, we have 2 hydrogen here and only 1. But if you have a double bond here, it means that this carbon is bonded twice to a C. So if I look at this carbon right here, this carbon is bonded to an H, that H, and twice to a C, so you consider them as C and C. So this first carbon there, that's what it's bonded to. Now if I look at this one, this particular carbon, it's bonded to 2 hydrogens and a C. See, it's 2 hydrogen and a C. So it's obvious that the top one is bonded to 2 carbons versus 1 carbon. So this is your number 1. And this is your number 2. Because carbon has a higher atomic mass than an H. And remember, if you see a double bond, it means it's bonded twice. See a triple bond, it's bonded 3 times. Now let's look at this one. This carbon, right? This carbon is bonded to oxygen. Oxygen compared to carbon. Oxygen is heavier, so oxygen is number 1, carbon is number 2. Even if it's bonded to an oxygen next, you always start at the same level. And if things are the same, then you go to the next level and the next level. So you see here, the one are in opposite side. So if they're in opposite side, like we have here, so this is an E isomer. Let's try another one. And you have so many, by the way, in your book that are, and I put the answer key for them, so I really highly suggest you try them. So if I have a C, I'm going to just do one more. C, so we have C, triple bond, CH. And in here, I have CH, CH2. And in here, I have a CO, H. And in here, I have a CO, OH. So I'm going to divide the molecule in 2 parts. Let's look at the green one right here. This carbon is bonded to 3 times a carbon. So it's like C, C, and C. This one here is bonded to a hydrogen and twice 2 carbons. So automatically you see this is triple bond with carbons. This is double bond, so this is definitely 1. This is 2, because carbon is heavier than hydrogen. Now, if I look on this side, they're both C's, so I can make a decision here. But let's look at this carbon right here. It's bonded to 2 bonds with oxygen. So we put OO and a hydrogen. This one is bonded to 2 oxygen and another oxygen. OO and O. So of course, this is number 1 and this is number 2. So again, in this case, it's an E isomer. So that's how you assign E or Z. So that concludes the part of cis-trans EZ isomer. So we're done with this half. Now, let's go to the other half, which talks about carbons, isomers that contain an asymmetric center. So this is page number 4, isomers with an asymmetric center. So the key word here is asymmetric. What is asymmetric? What does that mean? Well, here's an example. And I'm going to do the presentation with an atom, and then we'll talk about other things that you know in nature that are asymmetric. So you see here, this compound, CH3, so I'm going to use my better pen, CH3, CH, Br, CH2, CH3. If I focus on this particular carbon right here, that one, the pink carbon, what is it bonded to? See, it's bonded to a CH3. So one of the substituent is CH3, another one is bromine. So it has a CH3, it has a Br, it has an H, and it has a CH2, CH3. So you see, each of these substituents on this carbon is completely different. So you have 4 different substituents, 4 different things attached to this carbon. This carbon is called a chiral carbon, and it's also asymmetric center. So that carbon here with 4 different substituents, an atom with 4 different substituents is an asymmetric center. So that's what an asymmetric center means. And we also call it's a chiral carbon. So you have 2 ways of calling it. And we like to use the little asterisks here to show that it's asymmetric. Now, if I look at this carbon right here, it has 2 hydrogens already, so it's not 2 that are identical, so it can be an asymmetric. This one has 3 identical atoms, so it can be asymmetric. This has 3. So in this particular molecule, we only have 1 carbon that has 4 different substituents. So an asymmetric center is a carbon with 4 different substituents. So why is it an atom? What's the deal about it? So I'm going to represent it in a perspective like we did in the first part of this module. So if I want to represent this is an sp3. It's an sp3 carbon, so it's tetrahedral. So how do we represent a tetrahedral? We have 4 bonds. 1, 2, 3, 4. So in every tetrahedral, this is how you start with the skeleton. 2 bonds are 109, so it's a little bit more than a 90-degree angle. And this means that this atom, and this atom are all on the plane of the paper. This one means it's in the front, this one is in the back. So that's called the perspective. And now all I have to do is put the substituent. So I can put the H in the back. At this moment, I don't know the real position, but it's okay. And then I can put the bromine here. I can put the CH3 here, and I put CH2, CH3. So that's one way of representing this molecule. But this molecule also can be represented like this. So these two, if you look closely, the way I represented them, it's as if this were a mirror and they're mirror images of each other. So these two are mirror images, just like your hands. If you put your right hand with your left hand, they're mirror images of each other. And what happened is they can touch each other like this, but you can't put a right hand on a left hand and assume it will function like a left hand. So they're not superimposable. So it's like your hands. They're not superimposable. So these are called chiral molecule. Chiral means it has a mirror image. So it's a chiral carbon, which means that carbon has a mirror image of itself. And these two can be separated. They're not the same. Just like your right hand and your left hand, they're not the same. They're two different hands. So what do we call them when they're mirror images? These two, they're mirror images, they're called enantiomers. So what is enantiomers is two mirror image of a chiral molecule. So this is a chiral molecule. Chiral molecules means it has a chiral carbon. So it's a chiral molecule and it has a mirror image. So the two of them are considered enantiomers. Enantiomers is always a pair of molecules. They are mirror images. Enantiomers means the pair of mirror images, pair of compounds that are mirror images. Okay? So it's two stereoisomers. They're also called stereoisomers because we already said from the beginning that these isomers are stereoisomers. Stereoisomers, so isomers with an asymmetric center means they're isomer, there are two images of each other. So this molecule is chiral because it has a carbon with 4 different substituents, and any molecule with a carbon with 4 different substituents will be considered chiral molecule. Now, how do we name them? How do we call this one and that one? Just like we named the EZ cis trans, how are we going to name these things? Well, in here, we're also going to prioritize the substituents. So if I look at the molar mass, bromine is number 1. It's the heaviest. And then this one is number 2 because you have carbon attached to carbon, whereas here carbon is attached to hydrogen. So this is number 2. This is number 3. So the way you're gonna name them here is you're gonna go from 1 to 2 to 3, but here's the key thing. Your number 4, the hydrogen is the lowest priority, has to be in the back. So in this case, I put it in the back to make it easy for you, but we're going to do some examples where it's not in the back and decide how it works. So you first have to have your number 4 substituent in the back behind the page, and then you prioritize your substituent like I did, and then you go rotate. So here I'm going 1, 2, 3, I'm going counterclockwise. So if you go counterclockwise, we're not going clockwise, it's an S. So this is the S stereoisomer. In here, take a look. So number 4 is H, so this is number 1, this is number 2, this is number 3. So you see your 4 is still in the back, and going 1, 2, 3, you're going clockwise. So that's an R. And that's to show that they're not the same compound. So first step, prioritize your substituent, and then you're going to rotate 1, 2, 3, assuming that your number 4 is in the back. Now, what if the number 4 is not in the back? What do I do? So I'm going to bring another example, and I want you to look to this. So I have here CH3. I'm making another one. I'm putting here a bromine. I'm putting here in the back an OH, and I'm putting an H in the front. So you see, this has 4 different substituents, so this is definitely an asymmetric center. So this molecule, is it an R or an S? How do we choose? First step, you prioritize them. What is my number 1 substituent? Bromine is the heaviest one, so that's 1. This is 2, and this is 3. Bromine comes before oxygen. Oxygen is heavier than carbon. Now, in this case, my H is in the front. So, how do we read it? They tell you to switch them for a minute. You kind of imagine your OH is in the front and your H is in the back. So you have to kind of switch them from their position, 2 of them. You interchange the substituent. So if I interchange them and read it, whatever you read, the answer is the opposite. So if I assume the OH is not here but here, so I'm going to pretend the OH is not here. So here's my OH. How would that go? My 2 is here, so it would be 1, 2, 3. So that means clockwise, if my OH were in the front, it would be an R. But since my OH is in the back, this is an S. So let me repeat. If your number 4 substituent is not in the back, you interchange it with whatever is in the back. So that's what I do. I pretend that my OH is in the front now and the H is in the back. And I'm going to see how it rotates. If this were an OH, it rotates 1, 2, 3, it rotates clockwise. But the reality is, since I interchange them, it's the opposite, so it's an S. So you read the notes, you try to practice, you will figure it out. Now, this is called perspective. What chemists do is they have another way of representing these compounds. They use what we call the Fischer projection. So what is a Fischer projection, and how do we go from perspective to a Fischer? So number 5, I'm going to rewrite this. I'm sorry. I'm going to go back here. This one, for Fischer, it tells you your asymmetric center, you use a cross. So that's your asymmetric center. So you see this carbon right here, that's my asymmetric center. So Fischer uses a cross. So the horizontal means 2 bonds, and the vertical is also 2 bonds. So these are your 4 substituents. They have to go on each corner of this square. But for Fischer, these 2, the horizontal line represents 2 bonds that are coming out of the paper. They're in the front. And the one vertical is going in the back. So he doesn't represent it like this, just put wedges. There, we don't put wedges and dashed lines, we just put this. But in your mind, you need to know that the horizontal line represents two substituents coming in front of the page, and the vertical one is two substituents going behind the page. So now, how do we put the substituents? Two of them you can put anywhere you want. So I can put, usually the longest chain, the longest carbon chains, I have CH3C, but I don't have another CH3, so I'm just gonna put CH3 here and the Br here. So it doesn't matter what you put in here. So what's left? We have the OH and the H. I have two choices. Either the H is here and the OH is here, or, so I'm gonna write both, and then I'll decide which one is the correct one. So I can put H here and OH here, or I can put H on the left and the OH on the right. The question is, which one represents this? The one that represents this must be the S. Okay, we already know that this compound, this stereoisomer, this particular one is the S. So my Fischer projection must be an S. Now let's look here. The H based on Fischer now is in the front. So let's look at our substituent. This is still number 1. This is 2. This is 3. So we're going 1, 2, 3. We're going clockwise. You can see that we're going clockwise, but the H is in the front. So if we're going clockwise and the H in the front, if the H were in the back, it would be counterclockwise. If I go clockwise, it's R, but since H is in the front, this is the S. So this is the correct one. This is not the correct one. Let me repeat one more time. Why is that? Because going from 1 to 2 to 3 in this direction, it's clockwise. But since H, based on Fischer, H in this position is in the front, the correct thing is it has to be in the back to read the correct configuration. We read it R because H is, as H is in the front. So if we were to put it in the back, it would be the opposite. So whatever you read, you take the opposite of it. So that's how we went from the perspective. This is the perspective to the Fischer projection. And I put it in the introduction of this chapter. I told you to try the extra practice tutoring activity that you have on page 187 all the way to 189. So please try to do that. It helps you go through these conversions from one form to another. Let's try one more, okay? So now I'm gonna do the other way around. I'm gonna put a Fischer projection. So here's a Fischer projection. And I want to turn it into a perspective. So first of all, I need to read, what is this? Is this an R or an S? So my substituent number 1 is O. This is 2. This is 3. So I'm going 1, 2, 3, which is clockwise. But again, since H is in the horizontal position, it means it's in the front, which means whatever you read, you have to do take the opposite. So this reads an R, but it's really an S because the H is in the front. So how do I represent this in a perspective form? So you always do this and this. You start with the 2 bonds on the plane, on the paper, which is a single line, and you put the wedge and you put the dash. The dash, I would put H in the back to know that that's my last substituent. And I want an S, which means I want to rotate counterclockwise. So I can put 1, 2, 3. So this is 1. 2 would be CH2, CH3, and then CH3. So you see that this is 1, 2, 3. So that's an S. That's the same as this. That's how you go from Fisher to perspective. Now, so far, we covered atoms. You see here, we said isomers with asymmetric center, but I put an S there. So I covered with one asymmetric center, and we can say we have the S and the R. And what are these called? They are the enantiomers, meaning mirror images of each other. But we can have one with more than one asymmetric center. So here's one example. Here's a compound, C, H, let's say CH3, sorry, CH3. And here I'm gonna put an H, a Cl. So you see I have CH3, HCl. So here I'm gonna put a C, CH3. So automatically on this end, I only have a CH3. On this end, I have a C, CH3. So I have two other substituents. So let's say I have an H here and an OH here. So you see that this has two chiral centers. See, this is chiral, and definitely this is chiral. See, you have OH, CH3, H. There are already three different ones, and this side is not like any one of these. And same here. So I have two chiral centers. So how are we going to name them? Or are these an R and S? So we focus on one at a time. This is my substituent number 1. Priority, chlorine is the heaviest one. Then it's either this carbon, so this is a CH3. Sorry about how it's written, so it should be CH3. So it's carbon bonded to 3 hydrogens, whereas here it's carbon bonded to oxygen and carbon. So it's obvious that this is the number 2 for this particular carbon. So for this one, chlorine is number 1, this carbon is number 2, and this is number 3. So we go 1, 2, 3, we're going counterclockwise. So this left carbon is an S. 1, 2, 3. And the hydrogen being in the back, so I'm good to go. Now let's look at the green one. The first substituent is oxygen. This is higher than carbon, even though there's a chlorine. So this is number 1. The second one, it's either this or this, and it's obvious that it should be this because it has chlorine. So that's my number 2, and this is my number 3. So I'm going 1, 2, 3, counterclockwise, and the H is in the back, so that's also an S. Now, what's the name of the whole compound itself? What's the longest chain? CH3, C, C, CH3, so it's 4 of them. 4 carbons, so it's a butane, and it has an OH, so that's butanol. Remember, the OH comes always, so this is butanol. And when we start numbering for naming, we start with the carbon, so we start here, so the closest to the functional group, so it's 1, 2, so this is definitely a 2-butanol, because the carbon that has OH is the second one. And then we have a chloro also here. So this is number 1, number 2, number 3. So it's a 3-chloro, 2-butanol. But we have to say what is the configuration of each. So this carbon, so if I start numbering again, 1, 2, 3, 4. So it's a 2S. See, the number 2 is S. And it's a 3S. So this is the name of this compound. It's 2S, 3S, 3-chloro-2-butanol. Now, how do we represent it in Fischer projection? You have two chiral carbons. Every intersection is a chiral carbon. So what you can do is put the longest chain, CH3, CH3, and I can call this my green one right here, and the pink one is here. So what's on the green one? You have all of this, but then it has OH and H. So the question is, should I put the OH here or the OH here? If I put the OH here, that would be number 1, 1, 2, 3. So it goes clockwise, and since the H is in the front, so that's an S, so that's correct. So the OH has to be here, and the H is here. And again, take a look. This is 1, 2, 3. 1, 2, 3 is clockwise, but since the H is in the front, it's an S. So this is definitely the S. And now for this one, the two substituents are H and Cl. Cl would be number 1. So if I put it here, 1, 2, 3, 1, 2, 3, that would be an S, and the H being here, so it's an R, so that's wrong. So I have to put my Cl on this side. So this is the perspective. This is the Newman, the Fischer. Perspective, Fischer. And again, if you look at your substituent, this is 1, this is 2, this is 3. You're going clockwise, but since the H is horizontal, it means it's the opposite, so that's also an S. And we already said it's an S. The last thing is to represent it in the Newman projection. See, you can look on this direction. Remember the Newman projection? This pink carbon would be the front. On top, I have CH3. To the right, I have Cl. To the left, I have an H. Behind the pink carbon is the green. And on the green, on the side where the Cl is, we have no H. And then on the other side, there is an H, and there is a CH3. So this is the Newman. So you have to learn how to go from Newman to Fischer to perspective, from perspective to Fischer to Newman. And I'm going to put a few practice videos for you to check to understand the difference. So if you have two chiral centers, you're going to present two like this. But the question is, how many isomers does this have? For one chiral center, we have 2. Remember, one chiral center, we have 2 enantiomers. For 2 chiral centers, what are the enantiomers? What are how many possibilities? And here's the answer. You have, I'm going to use the Fischer projection because it's easier. So this one, we put OH, H, HCl. I'm going to redo it. OH, H, Cl, H. And then I put CH3 here, CH3 here. Now the mirror image would be to put OH here, H, H, Cl, CH3, CH3. So you see these two are mirror images. Because they're mirror images, we call them enantiomers. So we already know that this is S, and this is R, S. So automatically the mirror image would be R and R for sure. The image would be the opposite. And then what we can do is we keep this the same, but we put the Cl on this side. So now the 2 H's are on the same side, and the OH and Cl are also on the same side. So you can see that these are also, so these two are enantiomers, and these two are also enantiomers. So you have two sets of enantiomers. So if I call this A, B, C, and D, so we're going to say that A and B are enantiomers. The word enantiomers means they're mirror images, and C and D are also enantiomers. Now, what is then the relationship between A and D? A and D, you see, they are the same here, but they're different here. So one of them is different. So this one would be S. This is R. And this one is R. And this is S. So you see, one of them switched. The S became an R. The S became an R here, and the R here, and the R here became an S here. So the top and the bottom. So A and D, as well as B and C, are called diastereomer. Okay, so these are the new terms. Enantiomers means mirror images. Everything that's mirror images are called enantiomers. But when you change one of them and you leave the other one intact, then they become diastereomers. And for the rule, how many isomers you have, the rule is 2 to the n power. So if I have, the n means how many chiral carbons. So in my situation here, we have 2 chiral carbons, so it's 2 to the second power, which is 4. So that's how we have 4 stereoisomers. Now, another thing about these, and you see it in your textbook on page 165, if your H's are on the same side, so the H's are on the same side, they are considered erythro. There's another term. So these are erythro, meaning that the H's are on the same side. But if the H's are on opposite sides, like this, these are called trio. Trio. Okay, so these have the H's on opposite side of the Fisher projection. So these are considered trio. These have the H on the same side, so they're considered erythro. Another thing that I skipped earlier, and I'm going to go back to it right now, is if you have, so what makes these chiral? If you take this molecule, you separate it and you put it, it has the tendency to rotate the light in one direction. So if you take a monochromatic light and you send it through a beam and make it go through this liquid or this compound, when it comes out, the angle of the light changes. So we call them we call them optically active. So what is an optically active molecule is you take light here, okay, so a source of light, and the light goes through at a certain angle, and the normal light will have, it diffuses in all the different directions. Now, if you put this molecule there, the polarizer, sorry, if it's a normal light, the light diffuses everywhere. If you put a polarizer here, what happens is the light will start going through one direction. So it comes out in a very specific angle. Now, what happened with these molecules, if you put them through the light, so there is the normal light, and it's all over the place, and then somehow you put it through a polarizer, it polarizes the light through this. So normally you would expect it to land on a screen to make a spot like this, let's say. So it goes through this and hits the screen, and you see something like this, if there's nothing in there. But with a chiral molecule, if I put a chiral molecule right after the polarizer, so this is my sample, so let's say this is an R, the light, instead of coming and falling in that, let's say, vertical manner, it will rotate. So the axis, as it comes through the sample, it rotates the light in a different direction. So that's why, that's how they knew that these compounds are optically active. So when you have an R or an S, they're optically active, meaning they change the direction of a polarized light, the angle of it. So instead of falling, let's say, without anything, they would fall perfectly vertical on the screen. In here, they deviate slightly from that vertical. They make a little angle. And that shows that they're optically active. So if I put the R, it will, let's say the R will create a light that lands like this, that shifts to the right. And the S will create a light that shifts to the left. So let's say this is the R, this is the S. The R molecule will make the light shift from the original angle to the right, the other one to the left. But if I put both of them together, the light won't shift at all. So if you put equal amount of these two, if you put 50% of the R and you add 50% of the S, the light no longer switch angle. So we call this, it becomes optically inactive. So separately, they are going to change the angle of the polarized light, but together they don't. So we call this a racemic mixture. So racemic mixture is a mixture of equal amount of the R and the S. So if you have equal amount, you are not going to see this rotation of the light, the polarized light. But the minute you put one or the other, the light will shift to the right or to the left. So that's what makes them special. They have this chiral property, and they are called optically active. Now, if I take a molecule like this one, let's say I have an OH, CH3, CH3, H, H. You can see that this carbon right here has OH, CH3H, and this substituent, so it's definitely chiral. And this carbon is also chiral. It has 4 different substituents. So what are the isomers or the stereoisomers of this? So remember, we do the mirror image. These are the enantiomers. And then we can switch them and the mirror image of it. So one thing about these 4 is these 2 have a plane of symmetry right here. So because they have a plane of symmetry, if you flip it over, it's exactly the same molecule. So in this particular case, if your chiral centers have the same type of substituent, you no longer have 4 stereoisomers, you're only going to have 3 because these two are identical. So these are called meso. Meso means you have 2 chiral centers, but the substituents are identical and they're mirror images, so you have perfect symmetry, which means if you flip this 180, you get exactly the same one, so it's the same molecule. Whereas these, they're not identical at all. They're perfectly mirror images, because if you look at, is it an R or an S? Let's look at this one. This is number 1. This is number 2. It's number 3. So we're going 1, 2, 3, which is R, but the H is in the front, so that's an S. This one should be an R, so because we flipped one of the substituents. So you see that these two are completely different atoms, different configurations, mirror images. And this one would be 1, 2, 3. So that's 1, 2, 3 would be R, but because the H is in the front, this is an S. S. So these are mirror images. So these are enantiomers. So this concludes these stereoisomers. I hope you understand the difference between meso and enantiomers. If you have the same substituent on the same atom, you're going to have meso compounds. One last thing about cyclic compounds, are they optically active or not? So if I take a cyclic compound like this one, so this is a compound where I'm going to put the substituents here. So let's say I have a CH3 here and a CH3 here. You see that this is a chiral center and this is a chiral center. You have 1, 2, 3, and an H in there. We're not showing it. So these two are definitely chiral centers, but you have a plane of symmetry. So this is an achiral molecule. It's not chiral because it's symmetric. But if we do this, we put CH3 in the front and an H in the other CH3 in the back, this is no longer achiral, so this is chiral. Why? Because one would be R, the other one would be the S. They are not going to be like this. These are mirror images of each other, so they cancel out the rotation of the light. So let's say this one rotates the light to the left, this one to the right, and because they're together, you don't see any different rotation. So that's the reason we call them achiral. Whereas these are going to be different configurations. So if they are not, if you don't have a plane of symmetry, it's automatically chiral. Now let's look at this one. If I have here a CH3 and a CH3, you see that this substituent is the same as this. So here we don't have a chiral center. So this is also achiral because you don't have 4 different chiral centers. Now, if I have this one, although they seem to be in opposite directions, still this substituent is the same as this. So both of these are achiral. So I want you to try different examples, and I'm hoping to see you on Zoom if you have questions during the office hour. So here, definitely, we have 4 different substituents, no matter how. So this is definitely chiral. So that's basically what you need to know. Hopefully, you will practice all of these things over and over and over until you make it perfect. Thank you.